So in this section, we're going to work with the trig functions using angles that are measured in radians. So it should be fairly familiar to you from what you've done in previous courses. The only change will be that we're using things like pi over 3 instead of 60 degrees. So I'm just going to make the list of things, of sort of critical angles for us to know about. The first one, 360 degrees, is 2 pi radians. 180 degrees would be half of that, it's a pi. 90 degrees would be half of that, it's pi over 2. 60 degrees, it's a pi over 3. 45 degrees is a pi over 4. And 30 degrees is a pi over 6. So I'm going to use those angles in particular because 30, 60, 45 are the numbers that showed up in the special triangles, which means that they have trig ratios that you can write as a fraction with some square roots in them. You notice that I've got pi, pi over 2, pi over 3, pi over 4. It would be nice to have a pi over 5 in there. So pi over 5 would be 180 degrees divided by 5, which I think is 36 degrees. So I mean, we could wedge that in there if you'd like as a nice base unit in radians, but this one doesn't have a special triangle ratio, so it tends to get forgotten. And we could do a pi by 7, a pi by 8, pi by 9, etc. But these ones, pi over 3, pi over 4, and pi over 6, are the ones that show up in those special triangles. So I'm just going to write those out for you. The one you would have worked with quite a bit, the pi over 2 corner there. And then we have a 1, 2, root 3 triangle. In this particular triangle was a 60-degree angle down here, but instead of 60 degrees, we're going to call that pi over 3 radians. And this one up here was a was 30 degrees, so we're going to call that pi by 6. The other special triangle that you would have worked with is the 1, 1, root 2. Which has a pi over 2 corner here because it's a right angle, and a pi over 4 corner in the bottom and the top. Lovely. So basically, if we're taking the sine of some angle, let's say sine of pi over 3. So I'm using SOHCAHTOA, right? Sine is opposite over hypotenuse. Cosine is the ratio of adjacent to hypotenuse, and tan is the ratio of opposite to adjacent. I'm just looking for this particular angle in my special triangles and then returning the fraction that goes with it. So a sine would be opposite over hypotenuse. Sine of pi over 3, you find pi over 3 in the triangle, you take its opposite side divided by its hypotenuse. So the answer to this would be root 3 over 2. Okay. Whereas if you did the cosine of pi over 3, cosine is the adjacent side over the hypotenuse. So you'd find pi over 3, adjacent is 1, hypotenuse is 2. So the cosine of pi over 3 should be 1 over 2. Now that's a good one to check to make sure that this is making sense to you and that your calculator is set up correctly. If you tap on the DRG button, or you might have to use your mode settings in order to put your calculator in radians. So somewhere on the screen there will either be an R or it will say RAD, rad for radians. If you do that and you actually put in the number pi, or you find the pi button on your calculator, push it, divided by 3 equals cosine of that equals, it should give you 0.5 if you have everything set up properly. So you can do that to double check. Just to do a tan one, just so that we're thorough here, tan of pi over 4. Well, you find your pi over 4, and then tan is opposite over adjacent, so 1 over 1 would be 1. So you can check that one as well. Find your calculator, push the pi button, don't approximate it, actually hit pi on the machine. Divide by 4, tan of that should give you 1. So now that you've got the basics here, we can try it on some obtuse angles. And for obtuse angles, we're going to have to pull out cast rule, if you remember that. So cast rule looks something like this. And the idea is that in each quadrant, one trig ratio is positive, and in this quadrant they all are. So if I were to ask you something like the sine of 3 pi over 4, well, that looks a lot like pi over 4, but there's a 3 in there. What you have here is an angle in the pi over 4 family. So all of the members of the pi over 4 family return the same value when you sine or cos or tan them. The only thing that flip-flops between family members is whether they're positive or negative. So if I were to look at the sine ratio for the pi over 4 family, that would be starting here. Sine is opposite over hypotenuse. The value for this is 1 over root 2. Whether it's positive or negative, I still have to decide. So I take my pi over 4s there. I'm going to take this line that goes from 0 to pi. I'm going to split it into quarters. And then I'm going to do 3 of these pi by 4 wedges. So 1, 2, 3 pi by 4 is right there in that quadrant. And so if I look, that quadrant is up here where sine ratios are positive. This is a sine ratio, so my value should be 1 over root 2, positive. Now you can check that in your calculator. If you type 3 times pi divided by 4 equals, and then take the sine of that answer, you should get positive 0.707 something, 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 something. And that number, 1 divided by root 2, gives you 0.707. So you can check that as well to make sure it's working out. If I were to try a new example for you, do the cosine of 7 pi by 6. So looking at this one, this is in the pi over 6 family. So I'm going to go find that. There's pi over 6 here. Cosine is adjacent over hypotenuse. So the value of this thing is root 3 over 2. Now I just have to decide if it's positive or negative. So erasing this little diagram here. Talking about pi over 6s, so I'm going to take my pi and I'm going to cut it into 6 pieces. 1, 2, 3, 4, 5, 6. I'm going to cut the bottom pi into the same number of pieces. Alright, and I need 7 of them. So 1, 2, 3, 4, 5, 6, 7. That puts me here. That's down in this quadrant where only tan ratios are positive. This one is a cosine, which is not a tan, so it must be a negative value. So basically you're looking at the family of angles and then you write down the number based on the triangles, and then you use cast rule to decide if it's positive or negative. So just one final example. So we have one of each flavor. Let's do tan of, we haven't done thirds yet, right? Let's do tan of 5/3 pi. So I'm going to need a new diagram here. And I'm going to see that this one is in the pi over thirds family. So I find that. Here it is, pi over 3. Tan is opposite over adjacent, which gives me root 3 over 1. I'm just going to call that root 3. Take my pi radians and cut it up into 3 chunks, 1, 2, 3. Chop up the bottom as well. And I'm supposed to take 5 of them. So 1, 2, 3, 4, 5. That puts me here. That angle is down in this quadrant where only cosines are positive. This is not a cosine, so the value must be negative root 3. And you can check that on your calculator. 5 times pi divided by 3 in tan should give you a negative value. And the square root of 3 is 1.7-ish, 1.74, something like that. So you can check that out, make sure it works out. All right, so this one is going the other direction. In order to solve this, I'm going to have to arctan the other side. And so that's asking me what set of angles would return 1 over root 3 as my tan ratio of this particular angle. So in order to do this, I'm going to have to do 2 things when I'm working backwards. I'm going to have to identify which family of functions it is. And then once I've identified the family of functions, I'm going to have to decide which 2 quadrants have the right solution. So there'll be 2 that are positive and 2 that are negative. And I just have to choose the right family members for that. So if I've got tan of 1 over root 3, tan is an opposite over adjacent. This is the only triangle that has a root 3 in it. So for opposite over adjacent to be 1 over root 3, I must be working with the pi over 6 family. So based on the 1 over root 3 piece, alpha belongs to the pi over 6 family. Okay, so we have to decide which ones. So I'm going to draw that diagram for you. I'm going to go from 0 to pi, and I'm going to cut it up into 6 bits. And I'm going to do it to the 6 underneath as well. Okay. So this first one, that's pi over 6 right there. That would be 2 pi over 6. This would be 3 pi over 6, 4 pi over 6, 5 pi over 6. And now that I've got them on there, I have to be real careful with this particular one, because this one's sneaky. 2 pi over 6 reduces to pi over 3. That is not a pi over 6 family member, that's a pi over 3 family member. 3 pi over 6 is the same as pi over 2. That is also not a pi over 6 family member. So I'm going to erase all the ones that reduce. So that means that this one is gone, this one is gone, this one is gone, this one stays. Here would be 6 pi over 6. This would be 7 pi over 6, which doesn't reduce. This would be 8 pi over 6, which is the same as 4 pi over 3, so it's no good. This would be 9 pi over 6, which is the same as 3 pi over 2, so it's no good. This would be 10 pi over 6, which is the same as 5 pi over 3, so it's no good. And this one is 11 pi's over 6. So if you look at what's happened to all of these options, I ended up with one solution on this side above the axis and one on this side below the axis. One on this side above the axis and one on this side below the axis. So all I'm doing is taking this initial family member, subtracting it from pi, right? 6/6 of pi, take away 1 would be 5/6 of pi. 6/6 of pi plus 1 would be 7 pi over 6. Over here would be 2 pi, that's 12 pi over 6. 12 pi over 6, take 1 away, would be 11 pi over 6. That's how I'm generating these 4 family members. I'm hunting for the pi over 6 family member that is positive. You know, that this was a positive number here. So according to cast rule, tan ratios are positive in this quadrant and in this quadrant, which means I'm after this family member and this one. So what I've deduced then is that for tan of alpha to be positive 1 over root 3, alpha has to be either pi over 6 or alpha has to be 7 pi over 6. If you tried to use 5 pi over 6, you would get 1 over root 3, but you'd get the wrong sign. It would be negative 1 over root 3 because tan ratios are not positive in this quadrant. Same thing with 11 pi over 6. You get the right number, but it has the wrong sign. The last little complicating detail is that if I'd kept counting, right, 1 pi over 6, 2 pi over 6, 3 pi over 6, etc., 11 pi over 6, 12 pi over 6, the next one here would have been 13 pi over 6 if we kept going, if we looped all the way around. So you notice that it's in this quadrant, and it's a pi over 6 family member. That angle, 13 pi by 6, will return 1 over root 3 because it's a pi over 6 member, and it's positive because it's in this quadrant. It doesn't matter that I've wrapped all the way around the circle to get there. It's an option. The same thing would have happened if I'd come to here and then rotated a full circle, or another full circle, or another full circle, as many times as you like. As long as you do a complete circle, you end up at a valid solution. So this is correct, but it's not quite enough. Alpha could be this position at pi over 6 plus any number of full rotations. There's 2 pi radians in a full circle, right? We had that at the beginning. And the n is just saying you can take it once or twice or 3 times, 10 times, whatever you want. Any integer number of full circles. This, of course, applies down here as well. And I have my full set. All of the angles possible that satisfy tan alpha being positive 1 over root 3. And not only are there 2 solutions, two root solutions, but then there's an infinite number of rotations after that. So for this one, I have sine of an angle being negative 1 over root 2. So I'm going to have to arc sine that thing in order to solve this particular question. And whenever I use arc sine, arc cos, or arc tan, I have to generate the 2 root solutions plus as many rotations as I'd like. So to solve this, I'm going to have to decide first what family of functions generates the 1 over root 2 value, and then I'm going to have to select the 2 members of that family that would make the value negative. So I hunted my special triangles for a root 2. There it is. The sine ratio is an opposite over hypotenuse. So if I pick this angle, opposite over hypotenuse would be 1 over root 2. So this thing belongs to pi over 4 family. So if I draw myself a diagram there, So in order to generate these family members, I go to 0 and I step in a pi by 4. So that would put me here. 0 plus pi over 4 is pi over 4. To get to this one, 2 pi over 4, or 2 pi is the same as 8 pi over 4. So if I back up 1 in order to get to this location, that's only 7 pi over 4s. On this side, to get to this solution, the one on this side that's above the axis, I'd go 4 pi over 4s, right, like so. Back up 1. 4 back up 1 would be 3 pi over 4. 4 pi over 4 plus 1 would give me 5 pi over 4. So there I have it. Those are my 4 pi over 4 family members. I just have to pick the two that would generate a negative sign value. So signs are positive up here and up here. So the two quadrants where they're negative are the two underneath. So my alpha then, size of my angle, should be this one, 5 pi over 4, plus as many rotations as I like, or 7 pi over 4, plus as many rotations as I'd like. So I have my two root solutions plus an arbitrary number of rotations. So for our last example, I have a cosine. I'm going to have to arc cos the other side in order to solve for alpha. And when you arc cos, like the last two examples, you have to find the two base solutions plus an arbitrary number of rotations. So I'm looking for root 3 over 2 out of my special triangles. I can get that here. Cosine arrangements are adjacent over hypotenuse. So to get these two things into adjacent over hypotenuse, I'm working with the pi over 6 family. So I've got the pi over 6 family. All right, so I'm going to give myself a drawing. Keep drawing the crosshairs in there out of habit. Here's my 0. This is, well, if it's pi over 6 family, that would be 6 pi over 6, and this would be 12 pi over 6. So my family members are 0 plus 1, which would be pi over 6. 12 pi over 6 minus 1, give me 11 pi over 6. 6 pi over 6 subtract 1 is 5 pi over 6. And 6 pi over 6 plus 1 would be 7 pi over 6. So I'm hunting for the two family members that would result in a positive cosine ratio. Cosines are positive in this quadrant and this quadrant, so I'm looking for this one and this one. Therefore, my alpha would be pi over 6 plus an arbitrary number of rotations, or 11 pi over 6 plus some arbitrary number of rotations. So this shouldn't be any different than what you were doing in degrees, right? You would go to 180, subtract your solution, or 180 plus a solution. The only thing that's changed here is I'm using radians, which makes it look a little funnier because it's got pi's lying around all over the place. But the action you're doing is no different from grade 11. So good luck with the practice questions, and next section will be on things that don't follow special triangle.